Thanks, Adam. So on the next slide, what I want to talk about to begin with are some of the basic concepts that are important for both fluids and mechanics. And I'm not going to get into too much depth, especially on the fluids, but just cover some basic stuff. Velocity and pressure, I'm sure you're all familiar with. But the coefficient of drag is a very important number. As we saw earlier, it's proportional to the amount of force that you're going to need to push an object. And so if you can reduce that, you can really reduce the amount of energy necessary to keep that object moving. And at high speeds, actually, the effective drag is often, for instance, for cars, much higher than the amount of other resistance, such as wheels and through the drivetrain. So reducing that can really make a big difference. Occasionally, you're going to actually want to increase that, though, in certain implementations. So, for instance, on the Bugatti Veyron, which is the fastest production car in the world, there's an air brake that actually just by braking with drag creates the same amount of force as a regular car braking regularly, so with its wheels and brake discs. So there's also things like laminar versus turbulent flow. The picture on the right side of the screen is a picture of a turbulent flow. It's chaotic, and it's very good for mixing. It's good for transfer of energy, so heat energy, for example. But there are cases where you might want laminar flow, where turbulent flow would be a problem for you. And so being able to understand the differences between those and how you can control that. And finally, steady state flow versus transient flow. So steady state flow is just simply a flow that has developed and won't change over time if you don't change the inputs. Whereas a transient flow is always changing. And to give you an example of how this is useful, I just want to show a really quick video of how F1 teams use CFD to design their cars.
Really, a lot of our performance comes from aerodynamics. So that's one of our larger departments with around 40 people in it. One of the ways we try and both shortcut our time to market and to improve our performance is to use CFD. Now, CFD is computational fluid dynamics. It's effectively a digital wind farm. One big difference between the CFD and the wind farm is that we have the power to visualize flow and what it's doing. We break the car down into around 300 million cells, and we solve the equations that govern the airflow around the car to each one of those cells. You can see what's going on with the wind pattern as it becomes more living, so be the lowest pressures. The objective that will increase the downforce and reduce that. From that, we can determine the performance, we can develop the car, we can then design the full size components that go onto the car for the next race. We have to be thinking ahead, and at this time of the year, we're well advanced with our design of our car for next year. And indeed, even for 2014, and there are a lot of new regulations coming in, we're having to study the implications of those regulations, looking at the basic architecture that we need in our future cars.
So the takeaway from that video is that this team uses computational fluid dynamics and a supercomputer, in this case, to model their car, and it's actually much cheaper, even with the supercomputer, than it is to do a bunch of physical prototypes of an actual car, even a scale model. So they can do a lot of iterations on the computer and then test some of those in real life to analyze and get to the best car that they can get. So now I want to move over to mechanics, and before we'll have some examples for you in a minute, but I wanted to cover some of the basics here. Again, force and pressure I'm sure you're all familiar with. But there are other important factors such as stress, strain and deformation, stress-strain curves, and the factor of safety. And we'll get into all of those right now. So first, next slide, please. First, what I want to talk about is stress. It's basically just the pressure within a material due to a force being applied on it. It's easy to calculate for simple loads on simple geometries. So for instance, if you're just pulling at a cylinder, you can easily know what the stress within that cylinder is. You take the cross-sectional area, you know the force applied, that's the answer. But for more complex geometries, it's often totally impossible to calculate by hand. You can't find the stress on a car frame with a calculator and a pen and pencil. So what you need to do is you need to use finite element analysis. And the next thing I want to talk about is strain. And strain is...
Next slide.
Oh, next slide. Yeah. Sorry, actually, before I get to that, I want to talk about von Mises stress, which is a kind of stress in a way. It essentially combines the shear stress and the axial stress, normal stress that would occur in an object to give you one number, and then for ductile materials such as steel, aluminum, titanium, most metals, and most materials you'll work with, the von Mises stress is empirically the most accurate measure of failure. So it actually says, outside of these bounds, this material will fail. And so in most situations, you're going to use von Mises. In certain situations, if you're dealing with brittle materials or ceramics, something like that, you're going to want to use other failure criterion. But for most situations, you're going to want to use von Mises.
And von Mises is the default sort of that Inventor and a lot of other simulation tools use to report the results.
Indeed. So strain, I want to talk about next. It's very simple to understand. It's just the change in length over the initial length. So it's essentially just a measure of deformation. But materials don't deform linearly. You can't just pull on something and it will keep this same strain rate, we say. So to understand this better, I want to show a stress-strain curve, which is up next. And that's the relationship between the amount of stress you put on it, so essentially the amount of force over area, versus the change in length over initial length. And so you can see on the left side, this is a typical stress-strain curve for a generic steel. You would see something like this. Different materials will have different stress-strain curves, of course. Some of them won't have this little bump where yield strength is. Some will fracture much earlier. That's standard with a brittle material. But I want to talk about this because this is a good example of what you'll see in a stress-strain curve. So on the left side, there's a linear region, which we call the linear elastic region. Within that region, as long as you can pull and pull and pull, and it will deform in a linear amount. So if you pull twice as hard, it will deform twice as much relative to the initial size. And then when you let go, it will all return to normal. It will go back to where it started. So this is the region in which you're going to want to do most of your building. You generally are not going to want things to permanently deform. There are notable examples where you would, such as in a car frame, you want the frame of the car to yield, to take up a lot of that energy of an impact. But in most situations, you want to make sure that when you get off your chair, it's in the original shape it was in. It didn't bend permanently from you sitting on it. So you're going to want to usually use yield strength as the maximum criterion for safety factors, which we're going to talk about next. So safety factor is really important. Next slide. Oh, sorry, I apologize. Before I get to that, when you're looking at these stresses and strains on the computer, so within FEA, often people get a little bit worried because the default setting is to show you an adjusted displacement. So basically, the computer will exaggerate the amount of deformation that occurs in the part, just so you get an understanding of what's going on. You can change that to be actual. You can change that to be 0. But just know that often the initial setting is to adjust that either up or down. So you need to be aware that that's often not what it will really look like, and you can change the settings to see what it will actually look like. So in this situation, the stress is colored and the strain is shown on the right. So next up is factor of safety. So factor of safety is the amount of overbuilding, you could say, that you do for a piece. So when you're building something, you don't want to design it such that the highest load that it will ever experience is the yield stress, because it's possible that maybe somebody a little bit bigger than you expected, or a slightly stronger force, a little bit bigger earthquake, something like that comes around, or that your machining isn't exactly perfect. You can only say this with exactly perfect machining at a factor of safety of 1. So you often give a bigger factor of safety. You say a factor of safety of 2, meaning that you design it to be essentially twice as strong as you expect it to need to be. And a factor of safety of 2 is common within building design. We know how buildings react to all sorts of forces. We know what happens when you put a very heavy thing on, you fill a room with machinery, or there's an earthquake. We know how the building is going to react. So factor of safety of 2 is pretty good. For airplanes, actually, the FAA, which is the U.S. governing body for air flight, says that everything needs to be 1.5. A factor of safety of 1.5.
And an airplane, by the way, is what we're looking at here, in case you couldn't pick that up. They're flexing the wings, so Adam will say more about that.
Right. So on the right, you can see, you might think, a factor of safety of 1.5 is not that much. That kind of worries me. And I've been in airplanes before, seen the wings flap, and think, well, how strong is this really? And on the right, you can see exactly how strong that is. So this is before failure. you can see how much the wings are flexing. So if they've designed this for a factor of safety of 1.5, that means that when they say, oh, what's the maximum operating load we should expect, they're talking about flying through a hurricane, not just a little bit of turbulence. So in the same way, you want to be really conservative with your estimates of maximum force that you're expecting to see. And that's really important when doing this analysis, that you use the maximum forces, not just the normal expected forces.